Okay, here's section 2. These first few problems are going to be pretty straightforward. We're simply taking these exponential functions and writing them as logarithmic expressions. And so for this one, 3 to the x equals 7. The way I remember this is the base of the exponential function, which is 3 in this problem, is the base of the log also. So when I see 3 to some power, I know it's going to be log base 3. And then the way the rest of it works is, well, it's log base 3 of 7 is equal to x. Those two things are saying the same thing. And really not a whole lot to say about it, but 3 to the x equals 7 is the same as log base 3 of 7 equals x. So number 5, it's x to the 5th, the base is x. So for my log, the base is x, and then it'd be log base x of 3 is equal to 5. And this one, the base is e, so that would be log base e, in this case of x equals 9. Hey, hiccup. Or you could write that as the natural log of x equals 9. I would accept either one of those two. They're both perfectly fine. I don't care, although I would write ln x because it's less writing, but whatever floats your boat. Let's see, going in the opposite direction. So we're going from logs to exponential expressions. So going in the exact opposite direction, the base of the log is the base of the exponential function. So this will be 2 to the 5th is equal to x. And even though you could clean that up, 2 to the 5th is 32, I don't want you to do that. I want you to leave it as an exponential function. Don't simplify these. So if I want you to write it as an exponential function, it needs to remain exponential. If you change that to 32, then it's no longer exponential. So number 8, log base 1/2, so that's going to be 1/2 to the x power is equal to 7. And this one, the base is x to the e power is going to equal 2. And you can't do much with those, so there's our answers. Those take about 2 seconds. I like those problems. Don't y'all like those problems? I like those problems. Let's see, evaluate these. Now here I do want to completely simplify. I want to find out what this equals. These will be non-calculator. And so log base 2 of 64, the way I work this out is I'll set that equal to x, and then I'm going to write it in exponential form. So this is the same thing as 2 to the x is equal to 64. And then we need to clean that up. So 2 to the x equals 64. That's 2 to the x equals 64. I don't know if you know this, but 64 is 2 to the 6th power. And once you have the same base on both sides, then you can set the exponents equal. You get x equals 6, and that is what log base 2 of 64 is. Log base 3 of 1 over 27, I would again set that equal to x and say 3 to what power x is 1 over 27. Then I have to get those to have the same base on each side. 3 to the x, 3 to the x is equal to 1 over 27, which is 3 cubed. But then if you have 3 cubed in the denominator, you can bring that up to the top as a 3 to the negative 3. Now I finally have the same base on both sides, and you get x equals negative 3. So there's your answer. Good, good? Good, good? Good, good? Good, good? All right. Graphing. Now, if you remember with logs, first, let's identify the parent function. My parent function, if we strip away any transformations, my parent function is going to be simply y equals log base 2 of x. And in my opinion, graphing logs is the easiest one. I don't know why. It just always made more sense to me. And when you graph logs, I told you there are 3 things that you need to make sure you get. 1, all logs have a vertical asymptote on the y-axis. So I have a vertical asymptote on the y-axis, and then they pass through the point 1, 0, and then whatever the base is, in this case it's 2, so I go through 1, 0, and whatever the base is, 1. So I'm going to go through 2, 1, and then my graph of log base 2 of x does this. It starts off, hugs that vertical asymptote, then it comes off up and it kind of levels off. So there's my parent function. Now I've got to identify my transformations. I see inside with the x minus 1, and then I see outside, I see that 3. So my 2 transformations are X minus 1, that's the easy one. That's a shift to the right. I think shifts are a lot easier than anything else. I'm going to shift right 1. But before I shift, I see this 3 times the log of that stuff. The 3 is on the outside. That means it's going to change the y's. And we do the exact same that it looks like. So if it says 3 times something, then it's going to be 3 times the y coordinates. And I start with my parent function, which had the ordered pairs. I don't like where that is. I had the ordered pairs for my parent function. I had 1, 0, and 2, 1. So my x, y's for log base 2 of x were 1, 0, and 2, 1. But then I need to multiply my y coordinates by 3. So my x's are going to stay the same. I'm going to triple my y coordinates. So I have 1, 3 times 0 is still 0, 2, and 1 times 3 is 3. And those are going to be my 2 new points. Okay, there we go. So I plotted my 2 points. Whoops. It's 1, 0, and 2, 3. So 2, 3 is up here. And then I shift each one of those points to the right 1 unit. So this point right here is going to go right 1 unit. This point will go right 1 unit. And the asymptote needs to be shifted right also. So that asymptote is going to go to the right 1 unit. And this is my new graph. It's going to come up. Let's make it bold so you can see it easy. It's going to come up, follow that vertical asymptote, hit that point, and then it's going to start to level off. So there's our graph of log base 2 of x. Never actually gets level. It's always going up. It just doesn't go up as quickly as you move to the right. Let's see. Number 13, log base 3 of all that mess. Let's see, well, my parent function is log base 3 of x. I'm going to start with that. So if I start with log base 3 of x, and I'll list some ordered pairs for that. Ordered pairs for log base 3 of x, 1, 0, and 3, 1. And don't forget the vertical asymptote on the y-axis. Now I have to identify my transformations. So it's log base 3 of stuff. Let's see. Inside the log, I see that 2. I see this 1. And I see a 4 on the outside. That 4 is not part of the log. Notice how I closed the bracket for the log. That 4 is on the outside. So I see 3 transformations. And I like to list my shifts first because they're the easiest ones to see. Inside with the x, I see a plus 1. So that's going to go to the left 1. Outside, I see a plus 4. So that's going to go up 4. And then inside, I see the times 2. Now, if it's inside, you always do the opposite of what you would think. Like when you see plus 1, right is what comes to mind, but you actually go left. So when I see times 2 on the inside, we're actually going to do the opposite, and we're going to divide, and it is inside with the x, so we're going to divide x by 2. And that's what we're going to do over here. I'm going to find the x divided by 2 first. My y coordinates don't change. So 1 divided by 2 is simply 1/2. Y coordinate stays 0. 3 divided by 2 is 3/2. Or if you want to say 1.5, it's the same thing. Okay, so those are my points I'm going to start with. Don't forget we do have that vertical asymptote. So let's draw my axes here. There we go. And I'm going to plot these points first. So I have 1/2, 0. So I have a point here. And then I have 1.5, not 0. What's wrong with me? That's 1.51. We didn't change the y coordinates. So now I'll plot 1.51, and that's where my graph is going to be originally, but then I need to shift up 4 and left 1. So each one of these points, up 2, 3, 4, and left 1. Up 2, 3, 4, left 1. And then the asymptote needs to be shifted also. Now if you shift a vertical asymptote up, it doesn't change, but going left 1 definitely does change. So I need to move my asymptote left 1, and here's my new graph for this log. It's going to come up following the vertical asymptote and hit those 2 points, and then it's going to start to level off. There we go. Good. All right, finding domain. Now remember, domain of a log is a lot like the domain of a square root. The only difference is you cannot include 0. Whatever's inside your log must be positive. That's the rule for the domain of a log. So whatever's inside must be positive. which means I'm simply going to say 3x minus 7 must be greater than 0, and we solve the equation. This one's kind of nice. Add 7, divide by 3. So I'll get x is greater than 7/3. I am a fan of interval notation, so that's going to be starting at 7/3. We will not put a bracket because I'm not including, it's not equal to, and we will go forever to the right towards infinity. So there's x is greater than 7/3. Let's see, I think I had one more in this section. Yeah. Okay, log of 9 minus x squared. Again, the inside must be positive. 9 minus x squared must be positive. Now, this one's going to be a little bit more of a pain. This is one where we have to do that number line, the sign analysis. If you have an exponent larger than 1, you are much better off solving this by factoring. So 9 minus x squared is a difference of squares. I'll factor that by 3 plus x, 3 minus x, greater than 0. And it is not x plus 3x minus 3. The 9 is first. So make sure the 3 is first here. I will find the zeros. Negative 3 makes the first one 0, and positive 3 makes the second one 0. And that's going to be the center of my number line. So I'm going to have a negative 3, which gave me a 0, and positive 3, which gave me a 0. And then we plug in some test points. Something to the left of negative 3, maybe negative 4, something between negative 3 and 3, and something after 3. Those are my test points. And then we plug it in. I like to plug into the factored one. So 3 plus negative 4 is a negative number. 3 minus a negative 4 is going to be positive. A negative times a positive is negative. I'll plug in 0. 3 plus 0, positive. 3 minus 0, positive. 2 positives give you a positive. And then if I plug in 4, 3 plus 4 is 7. That's positive. 3 minus 4 is negative 1. That's negative. A positive times a negative is negative. And then you have to remember we are looking for numbers greater than 0, and numbers greater than 0 are positive. So I'm going to choose the interval that contains my positive numbers, and that's right here between negative 3 and 3. Do not include the zeros. We only want to be bigger than 0, not equal to 0. So the domain is everywhere between negative 3 and 3. Yeah. There we go.